So, welcome to this course on special theory of relativity. As you know, this particular topic, special theory of relativity, is a topic of general talk. Even non-physicists keep talking about the speed of light in vacuum, why things cannot be accelerated to speeds greater than that, and E equal to mc square, energy mass conversion. Students often think that we have so much of material around, so why do not we convert this material into energy and solve our entire energy crisis, all those things. And for physicists, it is a fantastic experience to learn the details of special theory of relativity. It gives a totally different perception of how we look at lengths, times, space, and that feeling, that inner feeling, which is not there in this the life that we live. We do not see those things, but then somewhere it gets connected. So, that is a really very interesting topic. And I had given very recently a course on special theory of relativity, basics of special theory of relativity in Hindi, and this course will be at a slightly advanced level. We will be talking of 4 vectors and electrostatics, electrodynamics, relativistic, all those things, and that is all given in the introduction page. So, I will start with the original Einstein's paper of 1905, where he has proposed this special theory of relativity. So, let me read the first opening paragraph of that. So, the title of this paper, in which this special theory of relativity is formulated, is On the Electrodynamics of Moving Bodies. Okay. The title is On the Electrodynamics of moving bodies. This is somewhat less known, that special theory of relativity which talks about space and time and length contraction and time dilation and all those things, starts with electrodynamics, and the title of the Einstein's original paper is On the Electrodynamics of Moving Bodies. Let me read it. This is English translation. The original paper is in German. Now, the first paragraph is, it is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. So, it starts with Maxwell's equations, electrodynamics and all that. Take for example, the reciprocal electrodynamic action of a magnet and a conductor. There is a famous Faraday's experiment, where you have a coil, you have a magnet, and then you move magnet into the coil, or move coil close to this magnet, and you see some kind of an EMF generated or electricity produced. So, referring to that, so I will just perform that experiment and then maybe proceed further. Take for example, the reciprocal electrodynamics action of a magnet and a conductor. The observable phenomena here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. It says that when you perform the experiment, you see that only the relative velocity is important. Whether magnet moves, coil stays at rest, or coil moves, magnet stays at rest, you get the same current or electricity generation or deflection in the galvanometer or whatever. So, it only depends on the relative velocity, but the two cases are very different once you go for the mechanism of producing that electricity. So, that is what it is said here. The observable phenomena here depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases in which either the one or the other of these bodies is in motion. For if the magnet is in motion and the conductor at rest, magnet is in motion and conductor, that means the coil, is at rest, there arises in the neighborhood of the magnet an electric field with a certain definite energy producing a current at the places where parts of the conductor are situated. So, this is the mechanism. If you move the magnet, this is the mechanism. It produces an electric field around, and that electric field drives current in the coil. But if the magnet is stationary and the conductor is in motion, no electric field arises in the neighborhood of the magnet. In the conductor, however, we find an electromotive force to which in itself there is no corresponding energy, but which gives rise, assuming equality of relative motion in the two cases discussed, to electric currents of the same path and intensity as those produced by the electric forces in the former case. So, let me perform this experiment and discuss these two mechanisms, and then we will proceed further in this. So, here is the coil, and the two ends of the coil are connected to this galvanometer here, and I have a magnet. This is a magnet and this is just a handle to hold the magnet. So, first let me move the magnet. The coil is at rest, so I am holding the coil and moving the magnet, and you look at this galvanometer, famous school experiment. So, when I do that, you can see that okay, as this magnet goes into the coil, there is a deflection. It is inside the coil and there is no deflection, only when it moves. When I bring it out, again there is a deflection on the opposite direction, and finally it goes to the middle position. So, that is it. If you move the magnet, around this near this coil, magnet going inside that space within the cavity and coming out, okay, you have deflection. Even if you move your magnet not going into the coil, but it is moving close to the coil, even then you can see the deflection. So, Einstein is talking of this experiment, and what is the phenomena, why this current is being produced. So, as I mentioned there, when this magnet moves, when I am moving this magnet this way, that way, this way, that way, there is an electric field around. Electric field is created by the moving magnet, and that electric field drives current in this. When I have this magnet here moving, it produces electric field, and that electric field goes here also, and that drives these free electrons, and that creates a current which leads to this deflection. The second case is when the magnet is stationary. So, I will just keep this magnet stationary and move the coil. So, I can move the coil, and you see that once again you have similar kind of deflection in the galvanometer. So, now there is no electric field. Einstein discusses that in this case, since the magnet is not moving, there is no electric field created around, but these turns here, the free electrons here, they themselves are moved, and because of that motion of the conductor in the magnetic field, you have current in the coil. So, these two are very different phenomena. Einstein is pointing to that. So, the puzzle is these two mechanisms are very different. A moving magnet or a changing magnetic field creates an electric field, which we call induced electric field. and then that electric field exert force on the free electrons of the coil, and then the free electrons start moving systematically in some direction, and that creates a current. This is one mechanism. Another is you have magnetic field, and then you move this conductor in the magnetic field, and then there is a force F is equal to q v cross b on the free electrons, and because of that force it moves. So, these are two different, totally different things. If your magnet is moving, if the magnet is moving, it is creating electric field, some kind of electric field, it is creating, depends on how it moves and all that, some kind of electric fields, and then you have conductor and you have coils. So, this electric field exerts force, and the equation is like this, governing equation is like this. In the other case, the magnet is fixed, it also has a magnetic field, this magnet also has a magnetic field, but then the current is not generated because of this magnetic field, but because of this electric field. Whereas, if this is stationary and if the coil, if that coil is moving, in that case it is this magnetic field which is here, that field exerts force on these free electrons, and that is governed by q v cross b, where v is this velocity. So, if this v and if this v, if they are same, then the current which results from these forces on the free electrons here and here, they are also same. So, Einstein smells that something is very intrinsically governing this, this cannot be a coincidence. So, there is something, some rule is there, some law is there, nature has yet another law which dictates these two currents to be same. So, that is mentioned in the first paragraph. Now, the second paragraph is examples of this sort, together with the unsuccessful attempts to discover any motion of the earth relatively to the light medium. So, now he is talking of attempts which were made, we will be talking about those attempts, in fact, one of them Michelson-Morley experiment, to measure the speed of earth in a supposed medium in which the light travels at certain velocity. So, the idea was that light is waves, and therefore, it will need some particles, some mediums to create disturbances in terms of which the wave will move forward. So, that hypothetical medium which was assumed to be there, it was named as ether. So, the whole universe is filled with this medium ether, because light can travel anywhere in the whole universe. So, those were the days, even including Maxwell's, they thought there must be, they were convinced that must be a medium which we are in general not able to experience, but it must be there, particles must be there which vibrate, and in terms of those vibrations the wave, the light wave travels. So, if that ether is all around and earth is moving through it with 30 kilometers per second, let us try to measure that velocity. So, there were the attempts, but they were all failed. So, examples of this sort, together with the unsuccessful attempts to discover any motion of the earth relative to the light medium in which light travels, suggest that the phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. So, whether it is electrodynamics, this coil and magnet experiment, or it is mechanics, vibrations of ether or wave propagation. So, everything is nothing is suggesting that there is an absolute rest. So, that is what he is writing. They suggest rather that, as has already been shown to the first order of small quantities, The same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. So, this is the starting opening remarks with which he then develops this special theory of relativity based on two postulates. One is principle of relativity and the other constancy of speed of light in vacuum. So, first thing is that okay. So, let me write. One is principle of relativity. So, what is that? It is that you do not have any special frame which you say that okay, this is the rest frame, this frame is at rest. You do not have an absolute rest or frame which you can call at rest. It is your choice. Whichever frame you pick, you can call it at rest or you can call it moving. And the laws of physics, as he said, laws of physics, all electrodynamics, optics, mechanics, everything, all laws of physics must be same in all frames of references. The whole theory is in terms of inertial frames, that is also important. It is not mentioned here, but this is also very, very important. I will just talk what is inertial frames. Okay. So, inertial frame means Newton's first law should be valid. If I have a frame xyz axis and a particle, and I know all the forces on the particle exerted by the sources are also known, exerted by earth, gravitational pull or Coulomb force or tension in the string or spring or friction. So, these are all real forces where you know what has created that force. The electric field has created force, magnetic field has created force, the tension has created force, spring compression has created force. So, these are the forces. So, I know the forces, and if all those forces add to 0 or there are no forces acting on the particle at all, its acceleration should be 0. So, the frames in which that happens, 0 force means 0 acceleration. They are called inertial frames of references, and then the other frames which are there in which you do not apply any force and you see that there is an acceleration in the particle, or you apply forces and you see that you do not have any acceleration of the particle. So, those kinds of frames are called non-inertial frames. So, in non-inertial frames, Newton's first law is not valid, Newton's second law is also not valid, and if you still want to use F equal to ma, then you from your own side add some pseudo forces and then say that okay, F equal to ma, we can use it by including these pseudo forces which do not exist, but only because you are using non-inertial frame, therefore, you have to bring them in. So, those are. So, all our theory that we will be doing in this course will be only with reference to inertial frame of reference. We will not talk of non-inertial frames. The large number of questions will be there. What happens if the frame is non-inertial? How this equation will change and this and that? I will not respond to that. It is a totally different topic and totally different physics and totally different mathematics for that. So, we will confine to inertial frames. So, in all inertial frames, if you have a frame in which you do find that yes, without applying a force I do not produce any acceleration, it is an inertial frame. And then there is some other frame which is moving with constant velocity with respect to that, this is also inertial in any direction, constant velocity without changing the direction, axes are not rotating, and there is a translation, there is a displacement between this frame and that frame as time passes. So, you have a velocity, that velocity can be anything, but constant, fixed, no acceleration, then that frame is also inertial. So, for all practical purposes of our daily life, Earth's frame can be taken as inertial for many of the purposes, not all purposes, but many of the purposes locally, at least for some time. The earth moves with a constant velocity with respect to the sun frame. Sun frame is much better inertial frame. Earth also can be taken as inertial frame. That is our experience. If I put it here, it stays here unless I apply a force. If I do not apply a force, there is no acceleration on this. I apply, table applies, earth applies, the total force is 0 and there is no acceleration. So, this room, this table is essentially an inertial frame of reference. Some small non-inertiality is there, but okay. And then if I am moving in an airplane or I am moving in a four-wheeler with on a very smooth road, and if I perform an experiment there in that four-wheeler car and I perform an experiment here on this table, if I take this coil and this magnet and this galvanometer in the car, and while car is moving smoothly on a very nice road, and I still do this magnet going into the coil, coil going into the magnet, the same kind of deflection will be seen in the galvanometer as we see it here in this on this table. So, all laws of physics are same in all inertial frames of reference, and therefore, by doing any experiment in confined to one frame only, you will not be able to tell that whether that frame is moving or at rest. There is no idea of a frame moving or rest. You cannot determine it whether it is rest or it is in motion by doing any experiment. You can always say that this is at rest with respect to that, this is in motion with respect to that. So, that is the idea of principle of relativity. So, this is a postulate, that laws of nature are same in all inertial frames. Let me see in what language he writes the postulate. So, the same laws of electrodynamics and optics will be valid for all frames of references for which the equations of mechanics hold good. So, that was the principle of relativity. Then he puts another postulate, which is namely that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. So, light always propagates in empty space with the same definite velocity c, independent of whether the source is moving or not. So, essentially what it says is, or how we will write it, that speed of light in vacuum is c in all inertial frames of reference. In 1905, when this theory was formulated by Einstein, it was for inertial frames, but it was not explicitly mentioned there. And when he started working later, what happens in non-inertial frames, then comes that general theory of relativity, which comes out to be very, very different from this. Okay. So, since this was prior to that general theory of relativity, you do not see the mention here, but we will have to write that. So, this is one, and this is principle of relativity. All laws of physics, rather of nature, are of the same form in all inertial frames. So, this is principle of relativity. All laws of physics are of the same form in all inertial frames. The second is constancy of speed of light. Speed of light in vacuum. it's same in all inertial frames. So, with these two as postulates not to be questioned, of course, they are coming again from the experiments. All physics theories come out of experimental observations. Faraday did this experiment, so electrodynamics, and then the same current, whether you move magnet, whether you move this. Then experiments where people try to measure the speed of earth in ether and deduce from that that you change the frame and the speed of light remains the same. So, these kind of experimental observations have led to this postulate, but now it is a postulate. Now, we will not question it, we will of course discuss, we can discuss why this, but they are raised to the status of a postulate, means do not question them, and from here derive other things. So, that is the starting point, and from here we will derive all kinds of theories of relativity, but I will talk little bit of this experiment which he mentioned, unsuccessful attempt to measure the speed of earth in light medium. So, that part I will discuss in the next lecture, and then we will go ahead with this.